Okay, thank you to be here for the lecture of today. Just to recall in a couple minutes the concept of the observability, in particular the observability in the context of the nonlinear system. Yeah, we can see here, this is the lecture number 1. Basically at the end of the presentation, you can find this slide in which we can see 4 possible concepts. If you remember just really a few seconds, the concept of the observability for a linear system was a little bit, let me say, easy if you want. First of all, we have just one concept, not 4 possible definitions. We have just one definition. Here, of course, in this course, I didn't insist on the observability. I will not insist to. In fact, you can find here just some, let me say, look here, possible definition. I don't want to repeat, read if you want again, and a test which is in a theorem. But we can see that in the linear system, I would like just to emphasize, does this theorem here formalize in the form of test without demonstration, the condition are necessary and sufficient. This means if the test is positive, we can conclude everything. We can say when the system is observable and when the system is not observable. And we can see that depends of the structure of the matrix C and the structure of the matrix A. This means it depends what I am measuring, or we will see in this course also the structure of the output. In this course, we have seen just, let me say, a few cases. But anyway, we have seen many things about that. Rank is know what is in the rank of a matrix, and full rank. Now we will go in depth on this. Then we have seen very shortly the meaning or the test in case of linear system, but time variant. The difference here, I forgot to say here, the system here, time invariant. Time variant means parameters does not change over time. This is clear because we have seen how we can estimate R, L, and so on in the electrical system, which I am considering. The difference here is a little bit more complex, the test. But again, the linearity, because the system is linear, preserve the necessity and sufficient condition, the necessary and sufficient condition. This means also in this case, we can establish definitively if the system is observable or not. We have just, I don't want to say just the definition, but anyway, as condition is definitively clear what we are considering and what we can do, if and only if. This means. Let me go ahead with this case here, because it's the case of today. I told you a little bit about detectability, but it's not exactly the goal of the course. Detectability, observability, go in depth on the observability. This is a topic or their topics related to system theory. I have to use a little bit because today we will answer the question of last time. And the question was, how many parameters can I estimate using, last time we used just one measurement, current on voltage. For a given measurement, given number of measurements, number of sensors, how many parameters I can estimate? Basically means how large can augment my Kalman filter. Do you remember last time, the first time I considered the motor, considering just the augmentation, one parameter, R, do you remember? And then we consider another example with the desiccator, I think. And we consider R and L, no, R and C. And the question is, could I also extend it more in both cases, considering more parameters, without losing the observability? Moreover, I can measure the observability. This is more complex. At this moment, we are speaking about is observable or not. in the text which I recall now in linear system, variant and invariant linear system, we can say if the system is observable or not. About the measure of the observability, this is a little bit more complex. I don't have time to tell you, but we have literature in which we can say, we can state a little bit how the system is more or less observable. Intuitively, we can understand that increasing the augmentation, the variable which I want to estimate, we decrease the level of the observability if we remain with the same measurements, because the information must be split in different elements to be estimated. I mean, I cannot estimate everything which I measure a few things. That this is, let me say, something in life. Now we cannot obtain many things using a few tools. This is, but I don't have time to speak about the measurement of observability. We can do together, nevertheless, in the projects. The measure of the observability, I give you some keywords, Gramian. We have some indicators, but basically it depends how many variables I measured, clear, and it depends how large is the set of variables, parameters, everything which I want to estimate. It's clear. Information, let me say, divided, let me say, roughly speaking, the number of measurements divided the number of elements, element means parameter in the state, which I want to estimate. If I measure a few things, if I want to estimate many things, of course, this ratio is very low. Just to give them the feeling. It's not this the grammar. The grammar is more complex, but just to give you the feeling that if I want to estimate many things and have a few measurements, of course, it could be that the system remains observable from the test we will see also in the nonlinear system, but the level of the observability is very low, and this means the Kalman filter or any kind of observer, because the observability is not only for the Kalman filter as an observer, for any kind of observer. Here in this course, I presented the Lumberger observer, nevertheless, as an introduction of the Kalman filter, but I didn't tell you about the sliding mode observer, Lyapunov-based observer. But of course, here in my group, we are working also with different kind of observers. Yeah, in nonlinear case, in order to answer the question of last time, how many parameters can I estimate? Can I augment? I have to introduce a little bit or recall this concept here, and also the test. We are in the case of nonlinear system because the augmentation can generate a nonlinearity, as last time and before last time. Of course, I told you that this is the most difficult case because how possible to say I introduce artificially a nonlinearity because I introducing artificial as a parameter, as the Gaussian parameter. This means something which I don't know anything. The Gaussian parameter means I characterize the variable, the parameter in this case, the variable, let me say, because the parameter change over time, just using some Gaussian, let me say, characteristic. You remember basically the variance, no? And the mean value is 0. Of course, it's the nonlinearity or this parameter is more deterministic if I know something about that. It's a little bit more easy to estimate because I have something more deterministic. Moreover, do you remember the Kalman filter is in compromise between a deterministic approach and a stochastic one? If I don't consider one of both, of course, we are in a difficult situation. We will see also later some physical nonlinearity, how the system works better in any case, even though nonlinear. Look, in the nonlinear system, we have basically 4 possible definitions. We will see that we have just a test for this concept here, locally weak observable, which we will use now. Nevertheless, this is written basically also here, as I told you now. Nevertheless, I tell you very shortly why is nonlinear system we can use 4 possible definitions, but we don't have a reasonable test for all 4 definitions, but we have just for this one. This means we can say if the system is locally weak observable. I clarify what I intend, and this implies weak observable. Why in nonlinear systems we used 4 possible definition theoretically. Practically, again, we have just a test for this one. Practically means something which we can use. Locally observable means that I can estimate the system just moving around in like neighborhood locally. Let me say is in a point of the domain of the system. Of course, this is the most strong concept because let me imagine, is this enough to move a little bit around my working point to be the observability in large? Why that? Because if I am able to estimate moving just a little bit around the point, it's clear that this includes also if I move far away. I don't know if it's clear. If I move a little bit, I assume that I can estimate what I want. It's clear that I can estimate also moving far away. Why not? Because if I move close to the equilibrium point, this set is included in a more large set of possible trajectory or possible, displacement. Let me say, if you think about the particle system, which we already discussed, for instance, in the motor and so on. And look, we have another interesting concept. First of all, locally means more for us because then we speak about weak. Well, locally means basically the characteristics of a nonlinear system are local. I do remember also the convergence of the UKF. No? I told you we have to guarantee, excuse me, the EKF, extended Kalman filter. We have to guarantee that we are close to the solution. Close means locally close to the solution, because otherwise it could be that the Kalman filter does not work, does not converge. In nonlinear structures, all characteristics are local. I don't know if you remember. We cannot say that, of course, it could be. It could be that locally implies, as in this case, global. It could be. It could be. But not necessarily. Typically, the characteristics of a nonlinear system are local. This means we cannot say that in general the system is stable, globally stable. Could happen, but not necessary. What about weak? We can see the word weak is related to the input. I mean, in weak observable system means that the system needs inputs to be observed. Do you remember? This is also an important difference with the linear system, just to understand why we are using this different, First of all, here, the system is a linear, a time invariant, excuse me. And we say that the system is observable not globally. We don't distinguish between local observability and global observability. This means moving around in one region or moving large, the system is observable not in accordance with this test here. But not only. We can see that here the test does not depend of the matrix B. Depends of the matrix C and the matrix A. Depends of what I am measuring, and matrix A characterize the dynamics. Remember, the characterize the dynamics is the interconnection between the systems. Here is different because in a linear system, everything change also with the input. This means a system is weak observable if I need an input. This means here, why this is strongest, this possible definition? Because here, independent of the input. I don't need here to the input. This means if I don't need the input, this means it implies also in local weak observable, because this means that is I need in this case to put an input in order to see something in output. And this here implies weak observable, because if I moving around the possible equilibrium point, the possible about the equilibrium point I didn't tell you, but you understand what I mean, is my working point. Could be also in the trajectory, not only a fixed point. This implies also observable in large, but nevertheless weak. I need the input. And also here I don't need to be local. I don't need the input. Of course, this implies again the weak observability, or the system is weak observable. Nevertheless, the reasonable test which we have, reasonable means without conditions, is just for this condition here, for this definition here, it is written here, is based on the Lie derivative, and then we will understand better also everything again using some example. Let me see if I forgot to say something. We can see that how complex is the observability concept in nonlinear system. Nevertheless, we can say that locally is observable, and we can see that also I need the input to be to estimate the system. In fact, the test, then we can understand with the example a little bit better, is this one. I have a nonlinear system. This is the general form of a nonlinear system. It seems to be complicated, but I will show you in an example, and I will use MATLAB. What a O0, O1, O2, O n minus 1 is, I will show you in 1 second. The rank should be n, must be n, but please pay attention. The nonlinearity loses the necessary condition. This means if this is satisfied, if this condition is satisfied, isn't a theorem here. I put just information, but if you look in some literature, isn't a theorem. If the condition is satisfied, yeah, we can say something. We can say is observable. It could be that we have some condition to obtain rank equal n. I show you a little bit more in depth what intend. But it's just sufficient. This means says when is observable, but the theorem does not say when it is not. Remember the difference between sufficient and necessary condition. The necessary condition say when it's not, and the sufficient say just when is observable. This means if this is satisfied, also under some condition, we can say, this is important because it's constructive nevertheless. It's constructive because we can find some condition, under this condition, the rank is satisfied, but we say just if is observable. If this condition is not satisfied, we cannot conclude anything because in a sufficient condition. I don't know if you remember the difference between necessary and sufficient condition, but I will do some exercise. Now, in order to clarify what this O0, 1, O2, On minus 1 is, n up to or the predix n minus 1, I will use this slide here, but with the example, it's more easy to do an example than to explain what is written here. Because we are using here this L, which is the Lie derivative. I will show you what I intend with the Lie derivative. But look, the first row, this is in a row because X is in a vector, is the partial derivative of H, which is the output of the system. Very often is the relatively easy expression. Sometimes it's complex. I will show you when the Kalman filter is performed also in the output. I mean, if I consider a part of the model also in the output, I have a lecture on this. Very often it's just, do you remember last time 100? Oh no, we measure, I don't know, the current, or 100 or 010, I don't remember. Anyway, just a constant vector, no? And vector with vector. But could be also complicated. This is the O0, in accordance with what we have here. I show you the example. Then this Lie derivative, which is here, derivative of L toward f of h, again, respect of x. Please pay attention, in some books, we don't have this transposition. It depends of the notation. It's the partial derivative of this, it's the gradient. I show you the example of this h, it's the gradient. It's a little bit, the notation is strange, but in all books, you can find this notation sometimes without transpose. I show you the example, easy to understand. This means now I do the scalar product between this gradient here. The gradient is in a vector. I don't know if you remember in high school, in math. The gradient is in a vector, horizontal vector. I will do the scalar product between this vector here and f. What is f? It's the field. This means we will see it's in the color. Rho multiply color is in a scalar. And then I do, again, the gradient of this function here. And then I do recursively. Because this here, this result, which is a vector, I called O1. You remember here. Let me do the example because it's more easy to show. It's extremely easy. We have also the help of MATLAB. We don't have to do the calculation. Nevertheless, I show you some short calculations here, and then we will use MATLAB. I have to call, but let me. One second, I need. Now. This is the system which I am considering, just in general. I already clarify a little bit this structure here, just to repeat. Look now the system which I want to consider. I want to consider a system which is characterized. It's basically an RL circuit, but it's characterized by R, which is variable, and L, which is variable. This means I will show you how it looks like this test. I will do with MATLAB, but I will show how we can build the matrices roughly. because the calculations by hand are a little bit heavy. And then we will analyze using MATLAB the case in which I have just to estimate the resistance, and then I will augment the gain. Exactly what I will show you now, which I will estimate not only R but also L. Anyway, I will compare the case in which I estimate just one parameter and then the case in which I estimate two parameters. And we will see that change the conditions to obtain the observability. Of course, measuring U as an input, do you remember we need an input in any case, because otherwise we cannot, in the nonlinear case, we cannot consider valid the test weak, locally weak. And we measure the state current. And increasing the parameter to be estimated, we will see that the conditions is more and more restrictive. We can understand very easy in accordance with what I told you at the beginning. Let me now in this part here show you how we can calculate this matrix here, which basically is written in small compact form here. Look, what I am measuring is the current. H of t can be written in this form here. Now, of course, I can write everything in the form of 1, 0, 0 as a matrix C, which multiply current R of t, L of t. I can do also in this form here. But basically, this means H of t equal I of t. You remember, until now we have a C matrix C. In this case is 1, 0, 0 row, which multiply the column which consists of the state. Which kind of state? Current, which is the physical state, R and L, which they are, of course, they are physical elements, but it's something which we build because we need to estimate, for instance. We need because they change over time. And this is a possible approach to include what change over time is a possible Kalman structure. Again, the test of the observability is done not on the physical system, but on its representation. This is extremely important because we have to be able to answer if our possible representation is observable. This means if it's effective in the concept of an observer. Again, it's the observation which makes the difference. The physical system is, we don't know. We have just a representation. This is our representation in accordance with our goal. Assuming that R and L changes, if R and L changes, change the current. We can see the dynamic of the current depends of R of t and L of t. This means in the concept of an monitoring, if I don't want to use the word observation, observability, the current change also because R and L change. Clear, huh? Look at this equation. This expression here can be also written as a matrix C, which equals 1, 0, 0, matrix in a row, which multiply the column current R and L. Easy. It's so difficult. So. Don't worry for the examination. I will give you an exam. The goal must be achievable in control. Depending on your background, I will give you a project which is possible to be, let me say, performed. The solution will, in any case, the software which I uploaded in my study can be used for the project, just to modify in accordance with the new issues, the new question, the new system. It is difficult, nevertheless, for you, because it's new, something new for you. But did you hear about that? No. Did you hear about observability? That's okay. We are here, therefore, complementary study, something which is not seen. Otherwise, why we have to complement. Complement is we do something which we don't know. No, we complement. How is it possible to say in German? Complement. Say, I don't have something, I complement my knowledge. It makes sense. But it's difficult for you to follow. Okay, let me. Y O0 is exactly what I told you now, equal C. It's easy because if you do the gradient, C is always the gradient of the output. In linear case, directly. And in fact, we can see here that the gradient of this function here is the derivative of this function here, h, with respect to the current, which is 1. The second component is the derivative of this function with respect to r, with 0. And the third component of the vector is the derivative of the current with respect to L, which again is 0. I don't know if this is extremely trivial. Do you remember the gradient is the vector? The gradient is in a vector. Just to recall what is the gradient. Having a scalar function. Having a scalar function. Here we have a scalar function. H of t equal the current. The gradient of h of t with respect to this 3 variable. I didn't write formally here. But the state is current. We can see current, resistance, and inductance in L. I, R, and L. Is the vector which consists of the partial derivative. Do you remember in high school, partial derivative? Basically, the first component is the derivative of this function with respect to the current, 1. The second component is this function, current again, with respect to R, 0. What is the component number 3? Is this function, derivative of this function with respect to L, again 0. Basically, C, in a linear case, as in this case, because the output H is in a linear function. This is the current with respect to the state. The current is linear. The function is the current. Is in the H is in a linear. It's always C. A0 is C. What about A0 multiply F? We need A0 multiply F to build O1. A0 multiply F is this vector here multiplied this column here, which is the field of minor linear system. Look, the first component is the first equation. The second component is the second equation. And the third component is the third equation, let me say, because F is the right part, of F is the right part of this general expression. This means this component, this component, this component as a field in column form. I see you perplexed. Are you data science? What is your background? Data science, or what is your background? What is, yeah.
Yeah, I'm from sustainability science, so yeah.
Sustainability.
Yeah.
But vectors, fields, derivative, gradient is a little bit far away, no? I remember, probably I already told you, I remember the project with a student from sustainability. Probably I told you, Fisher, Kalman filter. We received also an award, the best paper award in a conference, international conference, for some years ago. You can find on internet if you look. Mercoeli Paolo, I don't remember, award, paper award. You can find this sustainability using Kalman filter. Anyway, this multiplied this in the sense of a scalar product is in a scalar. Which one? Is exactly this, because 1 multiplied this is exactly this, 0 multiplied this is 0, 0 multiplied this is 0. Now, what about y1? Is the gradient of this expression. And then I proceed. But of course, doing by hand is extremely complex. Let me call, and then I will show you how we can solve with MATLAB. Let me stop a little bit. Yeah, let me go ahead. You can see that we have to do the gradient of this scalar function here. And we have 3 elements. And then we have to redo again everything which I did to calculate O1 to calculate O2. Let me show you quickly, but I don't want to really be boring. Oh. Of course, this is the result because I have to multiply this again by f in scalar sense, this rho by f, which is a vector, and we will obtain a scalar, and then doing the gradient, believe me, I didn't do here the calculation, but we have this expression here. This scalar, the field, we obtain a scalar function, then we have to do the gradient. Of course, a little bit boring, and then believe me, I didn't do the calculation, but you can believe me. Let me do everything using MATLAB so we can conclude this part with some considerations. Which kind of consideration? I will try to compare. Yeah. Exactly this case with 3 states. This means with 2 augmented states. And we will see which kind of condition we need to obtain the rank of this matrix equal n, which is, these conditions are more restrictive than if I consider just one parameter, for instance, R. But you can try to do at home L. Now we can see that with respect to 3 parameters, we have a less restrictive condition because, of course, we have, let me say, with the same measurement, very important concept. In one case, we want to estimate 3 elements, current, R, and L. In the second case, we want to estimate just 2 elements. Let me see. Yeah, okay, let me open MATLAB. Probably I forgot to say something, but it could be that I will have in mind later. I can remember. Okay, let me open MATLAB. Let me share MATLAB. Because, of course, in this case, it's also possible the system is relatively compact. But for more complex system to do by hand, yeah, could be a little bit really, I don't want to say difficult, but boring, and this it could generate errors. Now, I will show you with MATLAB how we can do a nice analysis, which is also constructive, even though the condition is just sufficient, because sometimes really we can find why I'm using sometimes, I will clarify now, condition in order to obtain the observability. If the condition is not satisfied, we cannot conclude that the system is not locally weak observable because the condition is just sufficient. Okay. Let me see, let me share, let me move. I think this material one of this. This is too complex. I think it's this one. Yeah. Ah, okay, now I see. Test of the observability for the following system, exactly what I told you now. You remember here, after the symbol here, we have a comment. No? I forgot to say, and I would like to say now, a very important concept. The matrix which I presented now, this observability matrix, consists of the row O0, row O1, row O dot 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 O n minus 1. In our case, we have O0, O1, and O2 because we have a system of 3 states. Starting from O0, we have 3 rows. In general, is a matrix which is not necessarily squared. This is an aspect which I didn't emphasize until now, but we can see now. I mean, in this example, no. Because as long as we have one output measurement, we have a necessarily square matrix. But if you have, I have an example here later just to show you. If you have more than one output measurements, this observability matrix is not square anymore. About that, this is a technical aspect. It's a little bit too detailed now to speak about that. But I have an example just to flesh out, to show you what I am saying now. The example which we are considering in this course, the examples are always with one output, not necessarily always depend of the project which you choose. But of course, with one output measurement, state measurement, I can show you that we have just, let me say, a square matrix. If the matrix is not square, basically we can demonstrate that the matrix is a matrix which consists of more row than column. This means rank of this matrix means equal n, equal n means, I don't know if you remember this possible notation, in a full column rank. But anyway, I will show you practically what I intend a little bit in order to clarify this sentence here. Even though in our course we don't use much, I mean, I don't have example with, I have an example here to show you didactically what I intend with two, for instance, measurements. But typically, at least in our course, in our project, we have just one measurement out. But practically, no, very often we have more than one measurement. But with more than one measurement, it's easy. I told you before. Measuring more and more, of course, we increase the information. This means we increase the level of observability and the probability, please pay attention, the probability, using a very important word, to have a system which is locally weak observable is higher. As the reason is here. We can demonstrate, I have also on a slide, but I can use this. we can demonstrate that in our matrix, which consists of P rows and N columns, the columns is the number of the states. And the P, the number of row, is the number of the variable which I measured, a state variable. We can demonstrate that the determinant to be checked, you remember a little bit in math, to calculate the rank of a matrix, one method is to use the determinant. If the determinant is not zero, you remember a little bit in math, we say that the matrix is full rank. Now, of course, if you have let me say, in a long matrix, the theorem says this is enough to find one possible determinant of all possible combination of the determinant which I can find in this, let me say, vertical long matrix, not zero, in order to say that the system is observable. The practical reason is why I have to check all possible determinants. We have also programs that do that for us, of course, because very often, if this is the number, this is the number of all possible combination in an observability matrix. This means that the system, inside the system, we have at least one fact, which the information are transferred from input to output and then from output to input. Basically, the observability means, roughly speaking, that the system is observable, is invertible. Measuring the output and the input, I reconstruct the state. Look, here in our case, let me see. I made a mistake. I mean, P, of course, depends on the number of measured value, but it's the product between the number of measured value and the number of states. Excuse me, I told you just partially. We can see here. P is in a theorem. I don't have time to talk, but I give you this concept here, which basically states that inside this complex system, if I have more than one measurement, of course, the information to obtain the state using the output and the input, of course, it's the first and possible. You have to consider all possible combination, all possible paths in this connected system, because graphically you can imagine that the information to obtain the state could have many possibilities. And P represents the number of output state measured, in our case 1, multiply the number of states. This means 1 multiplies 3 is 3. You have to consider this factorial element. Divided again 3, n is the number of states. 3 minus 3 factorial. 0 factorial is 1. And then n factorial. This is 1. As I told you, this means square matrix, because we have to check just one determinant. But of course, if you have a more than variable, which I am measuring, we have many possibilities. And this is the number of all possibility which must be checked. All possible combination, which state all possible determinant in an, let me say, vertical long matrix. I show you a little bit in the slide here, but let me do the calculations. This command here states basically that after this command here, all elements which I am writing here are symbolic variable. This means as I did in the paper. F is basically the first in this representation. It's not so nice because it's not exactly what I did in the paper, but I show you what. I'm considering F just the first row of the field, which consists of 3 rows. O0, we don't need to do the gradient because it's easy, 1, 0, 0. I already told you. Now, what about O1? This diff calculate the derivative of what? Of this scalar element. You remember, this is the product between a scalar function. This is a scalar function of the element. Is the product between a row vector, which is here, 1, 0, 0, as I told you, and a column vector. To be precise, to do exactly what I did, I need here to define F in a different form. To remember, I need to define F as a vector. I have to put here exactly F equal this here, but I didn't do, I don't remember, because probably at the beginning I built this and then the lecture, because F typically is the field, it's not only the first element of the field. If you don't like, I will modify exactly as in the lecture. I mean, to be modified as in the lecture, I have to do so. I don't know if you agree. It's exactly as before. It's exactly as before. But now, in accordance with the notation which I used in the manuscript. If you want, I can proceed. So this means here is the first component of the gradient of O0. Here is the second. This means in accordance with the change I have to put F. Why is the second? Because the first element was the partial derivative with respect to I. I mean, diff is the function in MATLAB, which consists of 2 arguments. The first one is the function, the scalar function, which must be differentiated with respect to I. Here is the scalar function, same, but must be differentiated with the second variable. I mean, I am building the gradient with respect to the function is always the same. It's here. Once with respect to I, second component with respect to R, and the third one with respect to L. I am using the same notation as in the manuscript, because F was exactly the field, 3 components. It is in a vector of scalar functions. In this case, we have just in the first component something, the rest is 0, 0. Now, why is easy here to calculate? Because now I have to use this recursivity. I mean, O2 is exactly O1, but instead of O0, I have O1 here. I don't know if it's visible. I tried to clarify before a little bit. Question me if it's not clear, but now once I have one of them, I can proceed recursively in accordance with the definition, with the test, which came from a theorem, but we can consider also that test is not exactly a definition in the test. And here we calculate exactly the observability matrix, and then we do the determinant. I will comment now this. Let me compare now this test here with this test here, in which I am considering just an extended system, an augmented system which generates an extended system, but just with 2 variables, current and resistance, basically an augmentation of just 1 parameter. I changed the notation because we want to use exactly the notation of the manuscript. Mm. Why I calculate twice? Okay, once with R and once with L. Let me, yeah, as I told you before. No? Yeah, this is with L. No? I don't know if it's clear. We can see here is L. Both cases, the last two calculations, represent an augmentation of one parameter. In one case, R, and the second case, L. The first case is 2 parameters, larger. No? The system is large. In order to answer the question, increase the parameters, how change the condition of observability? Here we can see that some conditions are needed, more restrictive if I have a large system, but increase, yeah, I cannot increase more. For other systems, we lose. We cannot say that we lose because the condition is just sufficient, but probably we lose. Let me modify this and then let me discuss the results. Okay, this is commented at this moment. Okay, let me run the file. I hope no mistakes in these changes. It could be. Okay, no errors. O1, U2. This is the observability matrix in the example of IRL, 3 states, 2 augmentations. Look at the condition. ANS is the determinant. If you want, I can comment also this one. Probably you can see better. If you want, I can comment everything, but it's clear what I comment. You understand what I mean. If I put semicolon, I don't print this, let me say, results in the workspace. But I think we can. ANS is the last, basically after the definition, the calculation of OF, we have this debt without a name, and in this case, MATLAB say ANS. ANS is the answer of this command. The answer of this command is called O_F. Look, the determinant of F equal this one. Look, this one here, if you put in evidence here, you will have this. Did you agree? No, I see a mistake here. Yeah, up to 3, no? Yeah. Excuse me for that. Did you agree? If I put here in evidence you, this is the condition, the determinant of OF. This means we have to find when this determinant is not 0. Because if the determinant is not 0, we have a rank equal 1. Excuse me, full rank for the unique determinant which I have. Put in evidence this, I have to treat because here I have as an error. Look, but this expression here is the derivative of the current with respect to the time. I don't know if it's visible from here. Is exactly, again, try to imagine you, I put in evidence. It's very well written here. No? It's exactly the derivative of the current with respect to the time. Do you agree? It's a little bit written in another form, but here is written minus R divided L multiplied the current plus U divided L, but it's exactly the same which we have here. Positive vertical. This means everything is minus U, which multiply the derivative of the current with respect of the time up to 3, excuse me for the error. No? But it is irrelevant for the result, but should be up to 3 if I say when. Yeah, right. Now we have the condition which must be satisfied in order to have the observability. Look, first of all, L should be not 0, the y no sense. No? The expression no sense. But this reflects exactly that the form of the system, because I divided everything by 0. But not only, reflect also, even though if I don't divide, if I consider again L multiply the derivative of the current equal minus R multiply the current plus U, if L is 0, I don't have any dynamical system. This means I cannot work with the current. Dynamical system. You remember the concept of the differential equation. I need the changes. Everything collapses. Everything collapses in a scalar element. But anyway, this is a trivial. I mean, L cannot be 0. Very important for us that U cannot be 0. And very important, remember I told you about the weakness. This means that's something which could be, cannot be, but in any case, it seems to be not 0 U. Very important is the derivative of the current should not be 0. This means if I have, for instance, a constant in input, this is very important. In an RL circuit, I will wait steady state, excuse me, in voltage in input, because the input is the voltage. I will have a steady state somewhere, depends of the R and L, and a constant current. The constant current means the derivative of the current equals 0. This means I have to put the input in U, not only, for instance, the output of a controller or in a signal, but a noise, because I need necessarily change of the current over time. Otherwise, I cannot say the system is observable. But in any case, I can say that it could be that it works if I am able to estimate everything until the current is not in steady state, until the current changes. But of course, this is restrictive. Theoretically, we have infinite time because when the current is 0, if the voltage is constant, in infinite time. But in accordance with the level of the observability, in one possible measurement of the level of observability, exactly the value of the determinant, of course, we reduce the level of observability over time if, again, using a constant. Typically, very, very often, we put an artificial noise in input in order to obtain the derivative never 0 or relative high. Look what happens now in the second case. The second case is characterized by the estimation of R. The second case, let me see. I put semicolon. O1, OF, this is the observation matrix. This is the condition. It's exactly this. Here is enough that the current is not zero. Of course, L. No. Let me see. Yeah, it's correct. In case I want just to estimate the resistance, is enough L not zero as before, and the current not zero. I don't need the derivative of the current, but I need the derivative of the current here. If I want to estimate instead of R, L. I will discuss together with you. Why that? Because we can see here, no? Yes, yes, correct. I did no errors. Because again, this element here is the derivative. Here we are in the case of L, no? We can see. Here is the derivative of the current with respect to the time divided L. Why in case of L I need that the derivative for the sufficient condition? If the condition is not satisfied, no conclusion. But if it's not zero, I can say that the system is observable. Because if the inner with the derivative of the current with respect to the time are zero, try to image here L. The equivalent expression here is L multiply this expression here equals minus R multiply I plus U multiply plus U. If this derivative is zero, I cannot estimate L because I annihilate L. I mean, independently of L, if this is zero, I cannot see L in the equation. Kalman filter cannot see L because it's annihilated by this zero. L should not be zero in all cases because why I lose the dynamical systems. In this form here, I cannot divide it by zero. You can also interpret in this form here. Let me discuss a little bit. Therefore, this. No? This condition. Because if the derivative is zero, we have determinant zero. But what it mean? Mean that L multiply zero, the Kalman filter cannot have information about L. Because L multiply exactly this derivative, which is zero. This condition here is the less restrictive. This here concerning the augmentation of R, which is here. Because it's enough that everything, in this case, the current, which multiply R, basically is the same condition of here. Because here we have the derivative of the current with respect to the time not zero to estimate L, because in the system, in the physical system, which I consider L multiply this, what multiply L is the derivative. If this is zero, I annihilate, I cannot have information about L in the equation. Here it's quite similar, but the condition on I. The condition is on I, because if this is zero, I cannot observe R, because R is annihilated by the variable which is zero. We can see that in this both condition, we don't have U. This means I can estimate this R and L independent of U. Very important, nevertheless, for L, that this is not zero. And for R, that's the current not zero. Let me see if I forgot to say something. L, of course, is more a structural condition. It's not exactly related to the observability. I cannot divide it by zero. No, you know that. We cannot divide it by zero. To define the determinant should not be zero. Here is the condition to estimate L. Otherwise, I annihilate L. I mean, L does not appear in the equation. The physical equation is L multiplied the derivative equal this, what remain on the right. If this is zero, L is not in the equation. If I is zero, R is not in the equation. This means, nevertheless, it's constructive because we know something which we can do. For instance, put some noise in the input such that the derivative of the current is not zero. Let me see the last sentence for you. This I discussed. Okay, I think probably I forgot to say something. For next week, we will see in a couple of linear system. It could be that I am able to show you something about SIR system, this Lotka-Volterra equation, but in any case, as I told you, I'm an engineer. Just 1 second to conclude what we see next week. In any case, this, I hope that to show you also SIR system. I have somewhere, because we work a lot with the COVID fakes, prey predators, let me say prey predators model. Also, the identification of fakes in the internet, we did a lot of things. Look, here we have a nonlinear system in which the nonlinearity at this moment, it seems to be, and in this expression here, x squared and so on, it seems to be physically not documented. We will see that is easy because we have a deterministic knowledge. How it looks like the nonlinearity. This sometimes can be also considered when we have a constant with some knowledge about some deterministic knowledge about the parameter or constant parameter, better to say, to be estimated. Okay, I close now the lecture. I'm here for questions. Thank you. Let me show you. Thank you for your attention. If you have questions about the project and so on, but I need a couple of lecture in order to show you the nonlinear system and two basic variation, and then we can think about the project. Of course, the variation is thousands. This means we can do some variation also through the project. But what I will tell you is the basic, represent the basic knowledge to do also along different variations or a different form of Kalman filters. I would like to show you some variations, and then also, of course, the representation of the model in the output is also in a possible variation. But I will hold a lecture also in February. I don't know exactly the first week in any case, and then another day In any case, I will be here you can also attend the classes per Zoom and so on, or see again the lecture in YouTube. I will organize on Friday. The students, one student come to me on Friday to help me a little bit to organize this YouTube channel, because it's not only this course here that I have to structure a little bit. To upload the program or the lecture is not a problem, but I would like to structure a little bit better the channel. It's free. Okay, thank you for your attention. I am here for answering your question. Thank you.